Hi, this is Jeff Spencer, Math 135 instructor for the Community College of Denver, and this is a video lecture over some examples of the two-group hypothesis testing that we've done this last week or so. I'm just going to do a couple examples where we're looking at the hypothesis tests of two groups. When we test the difference between two groups, we can look at their means, which comes from quantitative data, or we can look at their difference in their proportions. So if we're doing their means, then we have a t-data formula here, and if we're testing their proportions, then we have a z-data formula here with the pooled estimate off to the right that we'll have to compute. So I'm going to do a couple examples, and while I read this problem here, I'm going to explain why I'm using which of these two particular formulas and processes. But remember, I'm going to go through the hypothesis test steps, which is to write, the first step is to write the null and alternative hypothesis. The second step is to compute the test statistic, which is one of these two formulas. And then the third step is to compute the p-value. And then the last step is to make our conclusion. If our p-value is less than alpha, we'll reject the null. And if our p-value is greater than alpha, we'll fail to reject the null. So let's read this problem. It says, Harris Poll conducted a survey which asked, how many tattoos do you have? Of the 1,205 males surveyed, 181 responded that they had at least one tattoo. Of the 1097 females surveyed, 143 responded that they had at least one tattoo. Test at the alpha 0.05 level of significance if the proportion of males and females with at least one tattoo differs. So the key thing on how I differentiate between these two formulas is, was I given a standard deviation and a mean? And I clearly was not. It just said of this many, this is how many had at least one tattoo. There was no mean and no standard deviation given, so I can't use any of this, and so I have to write my null and alternative and use this z-data with proportions. Okay, so I'm going to start putting that up, and it's going to take me a little bit, so I'm going to pause the video and it'll be up in a second. Step A, I've copied and pasted the null and alternative in here. It said, test at the level of significance as the proportion of males and females with at least one tattoo differs. So that means I'm doing the two-tail alternative, that the two proportions are not equal to each other. So the null is always that the two proportions are equal to each other, and the alternative here is going to be, let me write that in there, two-tailed. Alright, then that means I want to use this formula. So I'm going to have to compute the three p-hats, the p1 hat, the p2 hat, and the general p-hat. Now, since males came first, I'm going to mention that my males are going to be group 1 and my females are going to be group 2. So my p1 hat is going to be the 181 over the 1205. So I'm going to start typing this in. I'm going to pause the video again and it'll all just show up here in a second. I've computed the three p-hats. I did that while I paused the video so it wouldn't take so long. The p1 hat is the number of males that have at least one tattoo, 181 out of 1205.1502. P2 hat is the 143 divided by the 1097. That's 0.1304. And then the pooled hat, we take the two numerators, add them together, and the two denominators, and add them together, we get 324 over 2302 for a pooled of 0.1407. So now I'm ready to plug everything into the formula. My z-data is going to be my p-hat from group 1, my men, 1.1502 minus 0.1304. And then I'm going to divide by my p-hat, or p-pooled hat, 0.1407 times 1 minus 0.1407. And then I need to take that times 1 over the 1097 plus 1 over the 1205. Oh, I did those in reverse, but it doesn't matter. They're both in there. Okay, I should have put the 1205 first, but it won't matter. Okay, and then let's plug this into the calculator so that we can get our answer. Let me move over to the calculator. So actually, let me write this here first. I'm going to do a fraction. So document elements, equation, fraction, normal one. I'm going to write my top number and my bottom number. So I have to start with 1502.1502 minus 0.1304 0.0198. Write that down, 0.0198. And then I'm going to do the denominator here. So I have to do second square root of 0.1407 times parenthesis 1 minus 0.1407. And then times another parenthesis here, 1 divided by 1097 plus 1 divided by 1205. Get my denominator of 0.0145. Then take these two numbers and divide them. So I have 0.0198 divided by 0.0145. And it's a test stat of 1.3655. 1.3655. Okay, so finally got our test stat. Step C, let's do our p-value. Since we're doing a z-data, we're going to use normal CDF. Now this is a two-tail, remember, and for two tails it really just depends on what the test stat side is on. It's on the positive side, so that means I'm going to do normal CDF from 1.3655 to E99, and then I'm going to take that times 2. So let me type that into the calculator. So second vars, norm CDF, 1.3655, comma, E99. Take that result times 2, so don't forget to end the parenthesis, then times 2. And the p-value would be 0.1721. 0.1721. Alright, and that clearly is greater than alpha, which was 0.05. So step D, my conclusion. Conclusion is my p-value is greater than alpha, which was 0.05. So that means I will fail to reject the null hypothesis, which means if I had to interpret this, I do not have significant evidence at the 0.05 level of significance to show that the number of males with it, or the proportion of males with at least one tattoo is different than the proportion of females with at least one tattoo. So that's the final answer for that one. Let's take a look at this second problem here. Let me move this up a little bit. Okay, second question, it says, do people walk faster when they are getting on a plane, when they're arriving, or getting off a plane, departure? Researcher Seth B. Young measured the walking speed of travelers at San Francisco International Airport. He sampled 35 people departing and found a mean of 260 feet squared, 260 feet per minute, and a standard deviation of 53 feet per minute. He sampled 35 people arriving, and found a mean of 269 feet per minute and a standard deviation of 34 feet per minute. Do people arriving walk faster at the 0.05 level of significance? So this is saying, do people arriving walk faster? So a lot of people are going to think this is a right tail. Well, that would be true if you set up the people arriving as group 1. So that's exactly what I'm going to do, even though that information came second, because it's easier to translate the words when they say walk faster. That means greater. So arriving is going to be group 1, and departure is going to be group 2. So then we want to show that arriving is faster. So excuse me. No, we're walking faster. So if it's faster, their time is less. So I'm going to show that arriving, which is group 1, is going to be less than departure group 2. So let me throw in the null and alternative hypothesis here. So give me a second. So I have my null and alternative set up. We assume that the two. Oops, I have the wrong one. Excuse me. Let me fix that. This is the wrong one. We're using means here because we're given means and standard deviations. Okay, now I have the correct alternative and null hypothesis in there. Sorry for that. We're definitely testing means because we're given a mean and a standard deviation. So we're looking at, here is our null and alternative. We want to show that arriving group is faster, which means they have a less time than the departure group. So then it's on to do the test statistic, which is using this formula here. So I'm going to plug those numbers in, and I'll do that while I pause it. T-data formula. We have to get the mean from group 1. That's our arriving group. So he sampled 35 people arriving and found a mean of 269 feet. So we're going to do 269. And we can just put this all in group 1 like this. So the standard deviation goes here, 34 feet per minute squared. And then the sample size for group 1 was 35. Okay, then we minus off on the numerator the mean from group 2. He sampled 35 people departing and found a mean of 260 feet. Their standard deviation in group 2 was 53 feet per minute. We square that, and then we divide by the sample size there, which is also 35. Alright, so then we're going to write the top number, the bottom number, get this into our calculator, write them down. Okay, so the first one we have to do is 269 minus 260. That's 9. Jot that down. Okay, and then the denominator, we do second square root of 34 squared divided by 35 plus 53 squared divided by 35 again. That's our denominator, 10.6436. 10.6436. Or sorry. Yeah, 6436.6436. Take 9 divided by that. 9 divided by 10.6436, and we'll get a test stat of 0.8456. Okay, so once we get that, we have to do step C, which is our p-value. When we do our p-value, we do, for t-data, we do TCDF. Alright, and this is a left tail hypothesis. So, my error, I realized something here. This is not a time, this is a speed. So actually, this should be a right tail. I'm very sorry about that. Walking faster, I had it right and then I switched it, but this should be a right tail hypothesis because this is a speed, not a time. So people who walk faster have a higher speed, and it's showing that the mean is 269 minus 260. So we're definitely a right tail hypothesis and not a left tail. And the positive test stat kind of alerted me to that. Wait a minute, hold on. Group 1 has a higher speed, so that means that they're faster. So excuse my error, but I caught it, and things like that can happen to you as well. Be wary of that when you look at your test stat. Does it match with the tail? Does it make sense? And I was thinking time, not speed. This is a speed, feet per minute. So either way, we're right tail. So we're going to do 0.8456 E99, and I'm sorry, comma, the degrees of freedom, which is the two samples, the smaller of the two sample sizes, but they're both 35, minus 1, so 34. Let me type that in. So sorry about my error, guys. At least I caught it before it was too late. TCDF. We're going to do 0.8456, comma, E99, comma, the degrees of freedom, 34. So give us a p-value of 0.2018. 0.2018. And that, for our conclusion, our p-value is definitely greater than alpha. Which was 0.05, so our conclusion will be to fail to reject the null again. Sorry about getting the wrong tail at the beginning there, but it was fixed. Faster on a speed means greater, And that's the way I wanted to set this up in the first place, was a greater, and because it's a speed. A faster speed is a greater speed. So just remember, when you're picking between the two formulas, the key words that you're looking for is means and standard deviations. If you can identify those things, then you're definitely using the T-data formula. If you cannot, then you have to do a proportion for each group, and then you're going to be doing the Z-data formula. So hopefully these examples help, and we'll see you next time.